In 1928, a quiet theoretical physicist proposed an equation that seemed purely mathematical. Hidden inside it was a startling implication. Nature might contain an entirely new kind of matter, not exotic dust from space, but a mirror form of every particle already known. At the time, no experiment had seen such particles. Many scientists assumed it was only a mathematical curiosity, yet only a few years later, evidence appeared in a cloud chamber photograph. The universe, it turned out, held antimatter. The prediction came from one of the most precise thinkers in modern physics, Paul Dirac. Welcome to Mattermosaic, piecing together the universe one discovery at a time. Today we explore how a theoretical equation led to astonishing predictions and reshaped our understanding of matter, energy, and symmetry. The early 20th century was a period of upheaval in physics. Classical theories began failing at atomic scales. Quantum mechanics emerged to explain microscopic behavior. Electrons behaved like waves. Energy came in discrete packets. Probability replaced certainty in fundamental descriptions of nature. Albert Einstein's theory of special relativity showed that space and time were interconnected and that energy and mass were equivalent. Physicists struggled to combine quantum mechanics with relativity. Existing electron models ignored relativistic effects or conflicted with quantum principles. Dirac approached this problem with unusual discipline. He believed mathematical elegance often pointed toward physical truth. Rather than modifying older equations piece by piece, he searched for a formulation that naturally satisfied both quantum mechanics and relativity. In 1928, he produced what is now called the Dirac equation. It successfully described electron motion at relativistic speeds and explained electron spin. Spin had puzzled physicists, but in Dirac's framework, it emerged as an intrinsic property rather than an added assumption. However, the equation contained an unexpected feature. Some solutions corresponded to negative energy states. Physically, this seemed impossible. Electrons normally possess positive energy. If negative states existed, electrons should continuously fall into them, releasing enormous energy. That clearly did not occur. Dirac proposed an interpretation that preserved mathematical consistency. He suggested that all negative energy states were already filled in the Dirac Sea. Because of quantum exclusion principles, ordinary electrons could not occupy states that were already filled. If one negative energy electron were missing, the absence would behave like a particle with positive charge. In effect, a hole in this sea would appear as an anti-electron. This was an extraordinary prediction. It implied every particle might have a counterpart with opposite charge and similar mass. The concept challenged existing ideas about matter and symmetry. Many physicists reacted cautiously. Some admired the mathematical beauty but doubted physical reality. Others suspected antiparticles might exist but be extremely rare. Dirac himself remained restrained. He emphasized that theory suggested the possibility, while experiments would ultimately decide. Experimental confirmation arrived in 1932, when Carl Anderson studied cosmic rays using a cloud chamber, charged particles passing through left visible condensation tracks. Anderson observed tracks identical to electrons but curving in the opposite direction. The curvature indicated equal mass but opposite charge. The particle was named the positron. It was the first confirmed antiparticle. This discovery transformed antimatter from speculation into measurable reality. It demonstrated that theoretical physics could predict unknown components of nature. Dirac received the 1933 Nobel Prize in Physics for contributions to atomic theory. His equation became foundational to quantum field theory. Later research discovered antiparticles corresponding to protons, neutrons, and many other particles. Modern particle accelerators routinely produce matter-antimatter pairs. Antimatter also plays a role in cosmology. Current models suggest the early universe should have produced matter and antimatter in equal quantities. Yet the observable universe is dominated by matter. Understanding why remains one of the central questions in modern physics. Researchers investigate symmetry violations, early universe conditions, and particle interactions to explain this imbalance. Dirac's personal style influenced his scientific legacy. He spoke little, often choosing silence rather than speculation. Colleagues described conversations where long pauses preceded brief but precise remarks. He valued clarity, logical consistency, and mathematical simplicity. His belief in mathematical beauty influenced generations of physicists. Quantum electrodynamics, particle physics models, and modern cosmological theories all trace conceptual roots to his methods. Even today, theoretical physicists often search for elegant equations when exploring new physical frameworks. Antimatter has practical applications as well. Positron emission tomography, commonly known as PT scanning, uses positron annihilation to create detailed medical images. What began as abstract theoretical reasoning now contributes directly to medical diagnostics and biological research. The prediction of antimatter demonstrates the deep relationship between mathematics and physical reality. Equations alone do not prove existence, but they can reveal possibilities that experiments later confirm. This interplay between theory and observation remains central to scientific progress. It also illustrates scientific humility. Dirac did not overstate his claims. He allowed evidence to accumulate and accepted experimental verification as the ultimate test. Science advances through this balance of imagination, rigor, skepticism, and measurement. Antimatter reminds us that the universe often exceeds everyday intuition. Mirror particles, annihilation energy release, and fundamental symmetries challenge common sense. Yet careful experimentation repeatedly confirms these phenomena. Understanding them expands not only scientific knowledge, but also our sense of what reality can be. The story also shows how individual insight interacts with collective effort. Dirac's theoretical prediction required experimental confirmation from other scientists. Modern physics continues this collaborative pattern across continents, laboratories, and disciplines. As research continues, antimatter studies inform fields ranging from astrophysics to particle accelerator design. Investigations into antimatter behavior may help answer questions about the early universe, fundamental forces, and possible new physics beyond current models. This is Mattermosaic, piecing together the universe, one discovery at a time. If this journey into the prediction of antimatter sparked your curiosity, share it with someone fascinated by the hidden logic of the cosmos. Tell us what scientific mystery you want explored next, and subscribe for more weekly journeys across the fabric of reality.